The characteristic function phi x of t of a random variable x is a map phi from the set of real numbers R to the set of complex number C, given by phi x of t is equal to expectation of exponent itx, and this can be expressed as u of t plus iv of t, where I is a complex or imaginary unit defined to be square root of -1, and t is a real parameter. Please, we know that ut, that's u of t, is equal to expectation of cos tx, while v of t is equal to expectation of sin tx. Note that exponent I theta is defined to be cos theta plus I sin theta. So if we apply this in exponent itx, so exponent itx will be cos tx plus I sin tx. So that if we now take the expectation of this, that will give us expectation of cos tx plus I expectation of sin tx, which therefore implies that u is equal to this and v is equal to this. Properties of characteristic function. Property 1. We know that the characteristic function of a random variable x at t equal to 0 is equal to 1. 2. The characteristic function of x at minus t is equal to the conjugate of the characteristic function of x with parameter t. 3. The characteristic function of ax of t, where a is a constant, is equal to the characteristic function of x with parameters at. 4. The characteristic function of a plus bx of t is equal to exponent I at times the characteristic function of x with parameter bt. 5. The absolute value of the characteristic function of x with parameter t is less than or equals to 1. 6. The characteristic function of x with parameter t is uniformly continuous on R. Theorem 1. If expectation of absolute value of x to power n is less than infinity, then the characteristic function of x with parameter t has a continuous derivatives up to order n, given by the kth derivative of the characteristic function phi x of t with respect to t is equal to expectation of ix to power k times exponent itx for k equals to 1, 2 to n. In particular, for t equal to 0, that's if we put t equals to 0, this will give us the kth derivative of the characteristic function at t equals to 0 equal to expectation of ix to power k. Since when you put t equals to 0 here, you have exponent 0, and exponent 0 is 1 times this. That will give us this. Proof. The kth derivative of the characteristic function phi x of t with respect to t is equal to the kth derivative of the expectation of exponent itx with respect to t. Please recall that the characteristic function phi x of t is defined as the expectation of exponent itx, and this is equal to the kth derivative with respect to t the expectation of this is the integral from minus infinity to infinity of exponent itx, then df. We are integrating with respect to the distribution function f. Since the integrand is bounded, we can interchange the derivative sign and the integral sign as follows, so that the k derivative of our characteristic function phi x of t with respect to t will now be equal to integral from minus infinity to infinity of the k derivative of exponent itx with respect to df. Now, differentiating this function k times, we obtain the k derivative of phi x of t with respect to t to be equal to integral from minus infinity to infinity of ix to power k exponent itx, then df. Putting t equals to 0, here we have the following. The k derivative with respect to t of our characteristic function at t equals to 0 will be equal to integral from minus infinity to infinity ix to power k df. Since when you put t equals to 0 here, exponent 0 will be 1. But this integral is equal to expectation of ix to power x. Then for k equals to 1, we have phi x prime of 0 equals to expectation of ix. That's when you put x equals to 1 here, you have expectation of ix, and since I is a constant, it can be taken out of the expectation sign, so that will be I times expected value of x, and the expected value of x is mu, so this is equal to I mu. And for k equals to 2, we are finding the second derivative at t equals to 0. That's when you put k equals to 2 here, this will give us expectation of ix all squared. But I squared is minus 1. So you can bring it outside the expectation sign to give us minus 1 expected value of x squared. From here, we can find the variance of x in terms of the characteristic function at t equals to 0. We recall that the variance of x is defined as expectation of x squared minus expectation of x all squared. But the expectation of x squared from here, in terms of the characteristic function, expectation of x squared will be equal to minus the second derivative of the characteristic function at t equals to 0. So when you put it here, this will give us minus phi x prime prime of 0 plus the first derivative, which is the expected value of x. You know from here, mu is the expected value of x. If you divide both sides of this equation by I, that will give us phi x prime of 0 divided by I equals to mu. And when you square that, that will give you phi x prime of 0 all squared divided by I squared. And you know that I squared is minus 1. So that minus will change this minus to plus. So the variance of x is equal to minus phi x prime prime of 0, that's the second derivative at t equals to 0, plus the first derivative of the characteristic function at t equals to 0 all squared. Example 1. Find the characteristic function of the binomial distribution with parameter p. Solution. We recall that the probability function of a binomial random variable x is given by f of x is equal to n combination x times p to power x times q to power n minus x, where x takes values from 0, 1, 2 to n. Then the characteristic function of x with parameter t is equal to expectation of exponent itx, which is equal to the sum of exponent itx times the probability function n combination x p to power x times q to power n minus x as x goes from 0 to n. Multiplying exponent itx and p to power x, we have this. Sum of n combination x, p times exponent it all raised to power x times q to power n minus x, where x goes from 0 to n. Observe that what you have here, this sum, is the binomial expansion of q plus p exponent it all raised to power n. So therefore, the characteristic function of our binomial distribution is this expression, q plus p exponent it to power n. Example 2. Find the characteristic function of the Poisson distribution with parameter lambda. Solution. We recall that the probability function of a Poisson random variable x with parameter lambda is given by p of x lambda is equal to lambda to power x exponent minus lambda all over x factorial, where x takes values from 0, 1, 2, 3 to infinity. Then the characteristic function phi x of t is equal to expectation of exponent itx, which is equal to the sum of exponent itx times the probability function lambda to power x exponent minus lambda all over x factorial, where x goes from 0 to infinity. Now multiplying exponent itx and lambda x, this will give us this. Exponent minus lambda is brought outside the summation sign, so this will give us exponent minus lambda times summation lambda exponent it all raised to power x, that's multiplying these two, all over x factorial, where x goes from 0 to infinity. Please note that this sum is exponent this. What you have here is the Maclaurin series expansion of exponent what you have in this bracket. So this will then give us exponent minus lambda times exponent lambda exponent it. Now multiplying the two, this will give exponent lambda into exponent it minus 1. So this gives us the characteristic function of the Poisson distribution. Example number 3. Find the characteristic function of the exponential distribution. Solution. We recall that the probability density function of the exponential distribution is given by f of x equal to lambda times exponent minus lambda x for x greater than 0. Then the characteristic function phi x of t is equal to expectation of exponent itx, which is equal to the integral of exponent itx times the density function lambda exponent minus lambda x, and the integral is with respect to x. This is equal to lambda being a constant is brought outside the integral sign to give us this, times integral from 0 to infinity, multiplying these two, exponent itx times exponent minus lambda x, that will give us exponent minus into lambda minus it into x, then with respect to x. Evaluating this integral with respect to x, we have the following: minus lambda all over lambda minus it exponent minus in bracket lambda minus it times x, and the limit of integration is from 0 to infinity. Putting x equal to infinity, that will give us exponent minus infinity, which is 0, then minus, putting x equal to 0, that will give us exponent 0, which is 1. So this will then give us minus lambda all over lambda minus it into 0 minus 1. 0 minus 1 is minus 1 times this will give us lambda all over lambda minus it. So the characteristic function of the exponential distribution phi x of t is equal to lambda all over lambda minus it. The inversion formula. Recall that the characteristic function phi x of t of a random variable x is uniquely determined given a density function f of x. Conversely, given the characteristic function of a random variable x, its density function f of x can be determined through a well-known formula called the inversion formula. For the continuous random variable, the inversion formula is this: f of x equal to 1 all over 2 pi integral from minus infinity to infinity exponent minus itx times the characteristic function with respect to t. And for discrete random variable, the inversion formula is this: f of x equal to 1 all over 2 pi integral from minus pi to pi exponent minus itx times the characteristic function, and the integral is with respect to t. Example number 4. Let us find the density function for the random variable x whose characteristic function is given by phi x of t equal to exponent minus half t squared. Solution. Recall that for a continuous random variable that the density function is equal to 1 all over 2 pi integral from minus infinity to infinity exponent minus itx times the characteristic function, and the integral is with respect to t. Now let us put in our characteristic function, and this will give us 1 all over 2 pi integral from minus infinity to infinity exponent minus itx times the characteristic function with respect to t. This is equal to 1 all over 2 pi integral from minus infinity to infinity. Combining these two, that is exponent minus itx times exponent minus half t squared, will give us exponent minus half into t squared plus 2itx with respect to t. This will be equal to 1 all over 2 pi integral from minus infinity to infinity exponent minus half into t plus ix all squared. Please, we make this, the expression inside the bracket here, a perfect square. When you make this a perfect square, so this will then give us, this power will become minus half into t plus ix all squared minus x squared all over 2, then with respect to t. Exponent minus x squared over 2 can be brought outside the integral sign, then times 1 all over 2 pi integral minus infinity to infinity exponent minus half into t plus ix all squared with respect to t. To evaluate this integral, we have to make a change of variable by setting t plus ix equal to another variable, say z. So let z equal to t plus ix. Then dt is equal to dz. So therefore our f of x will then become exponent minus x squared over 2 times 1 all over 2 pi integral from minus infinity to infinity exponent minus half z squared dz. Observe that what you have here is the density function of a standard normal random variable z. And you know that the integral of this function is equal to the square root of 2 pi. This integral is equal to square root of 2 pi. So therefore, f of x is equal to exponent minus x squared over 2 times square root of 2 pi all over 2 pi, which is equal to 1 all over square root of 2 pi times exponent minus x squared over 2. This is the density function of a random variable x with that given characteristic function. Example number 5. Find the density function for the random variable x whose characteristic function is phi x of t equal to q plus p exponent it all raised to power n. Solution. We recall that for discrete random variable, the inversion formula is given by this: f of x equal to 1 all over 2 pi integral from minus pi to pi exponent minus itx times the characteristic function with respect to t. Let us substitute for the characteristic function here. So this will then give us 1 all over 2 pi integral from minus pi to pi exponent minus itx times the characteristic function with respect to t. And this is equal to 1 all over 2 pi integral from minus pi to pi exponent minus itx. That's the binomial expansion of the characteristic function is this: sum of n combination r p exponent it to power r q to power n minus r as r goes from 0 to n with respect to t. This is equal to, we can interchange the summation sign and the integral sign to obtain 1 all over 2 pi summation as r goes from 0 to n in bracket of the integral from minus pi to pi exponent minus itx times exponent itr. Place the p exponent it raised to power r is the same thing as p to power r times exponent itr. So if we bring out the exponent itr to join with this, that will give us exponent minus itx times exponent itr with respect to t. Then n combination r p to power r, this p to power r is brought here, then times q to power n minus r. So this will then give us 1 all over 2 pi summation r from 0 to n of the integral from minus pi to pi exponent, combining the powers here, that will give us exponent minus it into x minus r dt times n combination r p to power r q to power n minus r. And this is equal to 1 all over 2 pi summation r from 0 to n combination r p to power r q to power n minus r. Please, evaluating this integral with respect to t will give us exponent minus it into x minus r all over I into x minus r, and the limit of integration is from minus pi to pi. Putting in t equals to pi and t equals to minus pi here, this will give us the following result. So f of x is equal to 1 all over 2 pi summation r from 0 to n combination r p to power r q to power n minus r times exponent minus I pi into x minus r all over I into x minus r minus exponent I pi into x minus r all over I into x minus r. And this is equal to 1 all over 2 pi summation r from 0 to n combination r p to power r q to power n minus r times, please note we can simplify the expression inside the square bracket here to obtain 2 sine pi into x minus r all over x minus r. I hope you can recall that exponent I theta is equal to cos theta plus I sine theta, and exponent minus I theta is equal to cos theta minus I sine theta. So when you apply that result here, that will give us this. Now, since r and x are integers, we are summing the whole of this from r equal to 0 to n. It is possible that this r and x is possible for r and x to be equal, and it is also possible that they are not equal. So, and since r and x are integers, x minus r will also be an integer. So let us see what will happen. We are going to consider two cases here: the possibility when r is equal to x, and the other possibility when r is not equal to x. For r equals to x, what happened? The term, let us call the term a equal to 1 all over 2 pi n combination r p to power r q to power n minus r 2 sine pi into x minus r all over x minus r. For r equals to x, what you have here will be sine 0 all over 0. Sine 0 over 0 will give us 0 over 0, which is indeterminate. So what do we do in that case? When this term or this expression is indeterminate, we have to take the limit as r tends to x, and that can be done by using L'Hospital rule. So applying L'Hospital rule to find a as r tends to x, we will obtain the following: limit as r tends to x of 2 sine pi into x minus r all over x minus r will be equal to, L'Hospital rule says that we should differentiate up and also differentiate down before taking the limit. Derivative of this of 2 sine pi into x minus r will give us 2 pi cos pi into x minus r divided by derivative of x minus r with respect to x will give us 1. So that will give us limit as r tends to x of 2 pi cos pi into x minus r. So as r tends to x, we can now put r equals to x here. So that will be 2 pi cos pi times 0, which will go to 2 pi cos 0. And we know that cos 0 is 1. So 1 times 2 pi will give us 2 pi. So therefore, a is equal to n combination r times p to power r times q to power n minus r, since 2 pi will cancel out in the expression for a. Now, for r not equal to x, the expression 2 sine pi into x minus r all over x minus r will be equal to 2 sine k pi all over k. That is, if r is not equal to x, that means x minus r will give us some integer. R is an integer, x is an integer, so x minus r will also be an integer. So let us denote this integer by k. So that will give us 2 sine k pi all over k. And please note that sine pi is equal to 0. Sine 2 pi is equal to 0. Sine 3 pi equals to 0. And in general, since k is an integer, sine k pi will also be 0. So 0 all over k is equal to 0. So let us call the second part b equal to 1 all over 2 pi, the sum over r not equal to x, n combination r, p to power r, q to power n minus r, times 2 sine pi into x minus r all over x minus r. So this sum will be equal to 0, since we have shown that for r not equal to x, that the expression you have here is equal to 0. So the whole of this will be equal to 0. But f of x has now been split into 2 parts, that is a plus b. And this is equal to f of x equal to, b is 0, so that means f of x will be equal to a, and which is equal to n combination r, p to power r, q to the power n minus r for r equals to 0, 1, 2 to n.